the larger the node, the higher connectivity it has in the system structure, as shown in the screenshot here. So in SDVSU, a particular color can be selected in order to highlight the nodes with large number of dependencies. A zoom in feature is also implemented, which depicts in more detail the selected cluster, nodes and edge information. So SDVSU's keyword search feature is an effective way for developers to quickly search for particular source code file. For example, let's type Bugzilla, and then where you can see all the Bugzilla related files appear here, right here. And then we also implemented a zoom in feature. For instance, let's say if you are interested in this particular area, you can see the smaller nodes and bigger nodes. For example, if you click that particular node, so that's going to show the information related to that particular Java file. So to enable the identification of landmarks, basically the prominent features in a district, in a region, in a cluster, so we propose two heuristics by leveraging the layout and distance attributes of visual clustering. So one is centroid based and size based. So centroid based means here the centroid plays an important role in force directed drawing, as it balances the forces of all the nodes in a cluster. So visually the centroid serves as a landmark of a particular cluster or a district. So in case of size based landmarks, the size of a node is proportional to its edge degree, which means the larger the node, the higher connectivity it has in the system structure. So structurally, the large node serves a landmark of the cluster. Okay, so as we seen in the demonstration, so the heuristics are implemented as options in SDVSU. So the two heuristics, centroid based and size based. So it is crucial to note that the landmarks identified by these two heuristics in SDVSU are merely static dependency based. So I will next present the quantitative inquiry to explore how this tool SDVSU identify landmarks, and then how to assist developers with those landmarks. The goal of our quantitative analysis is to tackle two main issues. One is quantitative operationalization of navigational landmarks and quantitative assessment of our SDVSU's effectiveness. So to allow for thorough examination, we take advantage of Mylin's detailed interaction traces over 800 programming sessions. So Mylin is an open source task management system whose monitoring facility helps record a sequence of events. For example, you can monitor edits, views, etc. a developer performs on the Eclipse environment. So every programming session is linked with its corresponding task. For example, it could be a bug report, it could be an enhancement request, and so on. For the quantitative analysis, we studied the latest release of Mylin, which is the version 3.7.1, which contains 2,405 Java files. So Mylin contains 893 sessions contributed by 31 developers and 751 software change tasks. So this table shows the empirical study data for our quantitative analysis. So the average number of steps involved in Mylin sessions is 79.8, which is considerably greater, which implies that Mylin's software change tasks are more difficult and the navigations are more concentrated in that fewer files are visited per session, which is the 3.7. So the revisit ratio is over 95%, which means it is calculated as this 76.0 divided by 79.8, which gives you 95%. So this is from the navigational perspective. So this is the revisit ratio is 90%, which is calculated by dividing 3.3 divided by 3.7, which is 90%. So this is from the file access perspective. So these numbers, 95% and 90%, are significantly greater, which shows that revisiting is indispensable during software code navigation. This is a hypothetical code navigation scenario. So for example, in this scenario, a particular developer is navigating through different Java files, and then the developer is heavily relying on this landmark file to reach some other files. And then in this scenario, there are two separate landmarks, so developers using these two landmarks in order to solve particular maintenance task or activities. So in this scenario, so developer is not at all relying on any landmarks. In order to measure landmarks quantitatively, so we adopt the navigational cycles observed in Mylin sessions. So a cycle is defined as a series of files accessed by the developer beginning and ending with the same file. So for example, if the developer accesses, let's say for example, a cycle of ABCA. If the developer accesses file A, then B, then C, then A. So it's basically a cycle of ABCA with the length k equals to 3 is formed. So another scenario. So let's take A, B, C, A, C, E, F, B for example. So although A, B and C form cycles, only A is registered as a landmark. So the B cycle goes beyond the window size, which is 4, whereas C cycle is not long enough. So, and also please note that the maximum window size is 4, which is n equals to 4. So k equals to 3 here. So it's based on the observation that longer navigation paths have greater potential to contain extraneous files. So we observe the similar phenomena in case of Mylin data. So here in the both cases, from left side and the right side, so the landmark file is basically the file A. So this figure shows the stepwise analysis of revisited and landmark files. So even though the developers revisit a large portion of Mylin files, for example, here 82.6%, less than a half of the revisited files form cycles of length k less than or equals to 3 within n less than or equals to 4 window. According to the manual inspection of randomly selected samples from the landmark files, we confirmed the high precision of cycle-based operationalization. So in other words, the landmark files resulted from the cycle analysis are indeed referenced frequently by software developers in performing change tasks. So thus we take this 38.94% of the code files to be the answer set to assess our tool SDVisu's effectiveness in extracting those landmarks. Following the centroid-based and size-based heuristics, our tool SDVisu identifies 284 landmark files from Mylin's codebase compared to the 937 landmarks in the answer set. The SDVisu's precision and recall is 60.9% and 18.4% respectively. So this shows that the SDVisu is fairly accurate in recognizing the navigational landmarks, but its result coverage needs to be improved. To gain concrete insights into SDVisu's effectiveness, we specifically consider those software change tasks that have the contributions from both a single developer and multiple developers. So for the same task, a landmark file is referenced by either the same developer or different developers. So we therefore can use this analysis to assess the extent to which SDVisu extract the concept-driven landmark. This table displays the contingency table of the chi-square tests. The results are statistically significant, so the degrees of freedom is 1 and chi-square equals to 4.6, and the p is 0.032, and with this inferential test is performed at alpha equals to 0.05 level of statistical significance, so which indicates significant associations exist. So in this table, positive and negative signs show positive and negative associations, so it can be inferred from this table that the landmarks identified by SDVisu support the single developer in a positive way, whereas the landmarks identified by other means can be of positive influence on different developers working on the same task. So in this sense, the concept-driven landmarks are best recognized by methods other than our tool SDVisu. So these are some limitations of our quantitative analysis. So although SDVisu is promising in identifying the landmarks, other means needs to be explored in order to increase the coverage, and developers' code navigational idiosyncrasies could also be variable to consider. That's one of the limitations, and also the selection of parameters, especially the value of the k value which is less than or equals to 3, and also the n value. And also one of the important factors is the developer's experience. So it plays an important role, as skilled developers are observed to have longer navigation. Although tools are only part of the complex nature of software engineering work, it is worth discussing how our findings can inform the tool development. So we present here 3 design guidelines that help to integrate visual clustering into any software development environment. For example, interactivity. The tool shall enable developers' interaction with it, for example, zooming into a more focused portion of the code base, and then multifaceted path exploration and explicit landmark mapping. So coming to the conclusion and summary, so recovering software legibility features is an important reverse engineering activity. So in this research work, we have explored the use of static dependency based visual clustering to uncover landmark files which can serve as reference points for developers' code navigation. So our work not only advances the understanding about extracting legibility features of the software space, but also illuminates principled ways to increase the tool support. So in the future, we plan to continue investigating the practical value of visual clustering in reverse engineering and program comprehension. So our immediate next step is to conduct qualitative analysis to gain further insights into developers' code navigation behavior. Also, we plan to provide contextual information, for example, by automatically generating cluster labels and so on. So we have we also submitted our work to IEEE International Conference on Advances in Computing, Communication, and Informatics. So that's all about our work. So unfortunately, I cannot present in person. So if you have any questions, I'll be happy to answer any questions that you have now. Thank you very much.